I'm Eric Shidley, and this is Astronomy Fundamentalized, Lecture 4, Seasonal Changes. In this lecture, I'll talk about the constellations, the origin of the seasons, and the curious motion of the sun throughout the course of our year. This is an image of the night sky produced by the Google Sky application, and it shows a number of the constellations whose names might be familiar: Perseus, Cassiopeia, Andromeda, Triangulum, Aries, and so on. We all know that the identification of the patterns that are the constellations of stars come from ancient astronomers who looked and saw those patterns and gave them names associated with mythical characters. Nevertheless, we continue to use the arrangement of constellations today in these sort of rectangular lines that you see drawn around the constellations. For example, the constellation Perseus involves a number of stars with lines connecting in order to make the character associated with the Perseus constellation. But because of the borders that are drawn around Perseus, the galaxy that we see on the far left, NGC 1582, is also considered to be part of the constellation of Perseus. And so the constellations in the sky are used by astronomers to identify different regions of space, or regions of the celestial sphere, we should say, because as the constellation Perseus appears to be a number of stars in close proximity to each other, the reality of the situation is that the stars might actually be at remarkably different depths. That is, if Alpha Perseus and Beta Perseus seem to be very close to each other in the constellation, one could be very close, and one could be much, much further away. That is, if we were able to move to the side in a fantastic spaceship that could take us far from the Earth, Perseus would not look like Perseus. It would be rearranged perhaps into some other constellation that we could identify. Nevertheless, the regions of the sky are identified according to their constellations, and when you go out to do your amateur astronomy observing on any given night, you can use the constellations to find your way about. So far as my knowledge of the night sky, it's sketchy at best. One reason being that I don't go out in the wintertime to observe the stars. I occasionally look up in a mad dash from the car to the house. But in the summertime, there are some constellations that I've identified and stars that I can readily find and point out to folks to demonstrate that I have some knowledge of the night sky. And the way it works for me is this. If I go out on any given evening and I can look for the Big Dipper, which is actually itself not a constellation. It's actually part of Ursa Major. But we all recognize the Big Dipper. Once I find the Big Dipper in the sky, I look at the front two stars that make up the Dipper, and from the bottom one to the top, I draw a line, and that points towards Polaris, the pole star, some call the North Star. And the arc of the handle of the Big Dipper arcs to a star that is called Arcturus. The bright star that I see by arcing from the handle of the Big Dipper is known as Arcturus. I can also identify in the summertime the three bright stars directly overhead late in the evening, which are known as the Summer Triangle, and therefore identify Rigel, Deneb, and Altair. I use these stars in order to figure out the locations of things that I might observe. If I'm looking for a satellite or if I'm expecting to see a meteor shower, I use them to get my general bearings in the sky. The thing is, they change from season to season, so my knowledge of the summer sky is going to be useless in the winter sky. The reason for this is that the Earth is in orbit about the Sun. Here we see the Sun at the center of the diagram with the Earth orbiting around in a counterclockwise fashion. In September, if I go out at midnight when the sun is down, that is on the opposite side of Earth from where I'm standing, I look up into the sky, I'll see the constellation Aquarius at midnight. If I go completely around half the orbit to the other side, which should be midway between January and May, I'll look up in the middle of the night and see the constellation Leo. Now, those who are born in September have the zodiac sign of Leo. The reason for this is that the signs of the zodiac are named for the times or the intervals where that constellation is where the sun is at noon. So if I'm born in August into September, then at noon, then Leo is highest in the sky. And that's accounting for that constellation. It actually turns out that there are not 12 signs of the zodiac, but in fact 13. And that they don't occur necessarily when they're supposed to. The reason is that the signs of the zodiac were identified thousands of years ago, and since then the Earth has done a little wiggle, bit of shifting in its orbit that has caused everything to be out of whack. Since the signs of the zodiac, so far as we can tell scientifically, have no effect, no tangible effect, then we'll simply use the signs of the zodiac as an amusement from day to day. Specifically being what our horoscope has to say about the events of our lives. As the Earth orbits the Sun, it brings about some important changes. The chiefest of those is the seasons. It turns out that it's true that the orbit around the Sun is not in fact elliptical. Is not in fact circular, but is elliptical. There is a time during the orbit of the Earth around the Sun when it is closer to the Sun and a time when it is further away, because the orbit of the Earth is an ellipse. Now, if we had a chalkboard and I drew this ellipse as accurately as I possibly could, and we paraded a bunch of people by at random and asked them what it was, they would immediately say that it's a circle. Because despite the fact that the orbit is elliptical, it's not really that elliptical. It is not very eccentric in the mathematical language of ellipses. So, although the Earth is closer to the Sun in the winter time and further from the Sun in the summertime, the winter months are still the colder months. The reason for this is that the Earth is tilted on its axis 23.5 degrees with respect to the plane of its orbit. This means that in the winter time, the northern hemisphere of the Earth is tilted away from the Sun. And in the summertime, the northern hemisphere of the Earth is tilted toward the Sun. The effect is shown here on the left-hand bottom left diagram, that in the summertime, the northern hemisphere gets more vertical rays of the sun. This is significant in two ways. One is that since the rays of the sun are more vertical, they have less atmosphere to pass through in order to get to the surface of the Earth, and so there's less absorption and re-emission. And also, because the rays are more vertical, you see the patch where the sunlight reaches the ground. There's just one beam of sunlight, let's say. That patch has a smaller area, so the intensity of sunlight per unit area is larger, as compared to the diagram on the right, which is in the wintertime when the sun is low on the horizon, accounted for by the fact that the Earth is tilted away from the sun. Then the sunlight comes at a more oblique angle and therefore has to pass through more atmosphere. There's more absorption and re-emission. And also, if I look at the circle on the ground where this ray of sunlight actually strikes, it's more elliptical. It has a larger area, and therefore the intensity per unit area is less. And so the sunlight is less intense in the wintertime. Naturally, this is reversed in the southern hemisphere because when the northern hemisphere is tilted away from the sun, the southern hemisphere is tilted toward the sun. So if I'm viewing the sun throughout the course of the year as the Earth rotates, then I'll find in the Earth's rotation the sun follows a path through the sky which is called the ecliptic. It's the plane of the Earth's orbit, and it's the path followed by the sun. It is inclined at an angle of 23 degrees with respect to the rotation of the Earth. In this diagram, the Earth is oriented so that its axis of rotation is vertical. So in the northern hemisphere, in the winter time, we see the sun on the ecliptic lower on the horizon, and in the summertime, we see it higher above the horizon. The point that we call the summer solstice is the point in the northern hemisphere that the sun rises to its highest point. The sun in the northern hemisphere will never be directly overhead, but at the summer solstice, the Earth is tilted most directly towards the sun at the summer solstice, and so the sun reaches its highest point in the sky. The winter time, the Earth is tilted most away from the sun, and the sun appears lowest on the horizon. At the vernal and autumnal equinox, they are the 2 days of the year when the length of the day and the length of the night are the same. we see that the sun on the ecliptic is midway between the point of the summer solstice and the winter solstice. As a result, viewed from the northern hemisphere on December 21st, the winter solstice, the sun will be at its lowest point on the horizon and will follow the path on the left-hand side of the diagram. On June 21st, the summer solstice, the sun will rise and travel as close to the zenith as it possibly can. And when we're midway in between, on March 21st and March 22nd, the sun will follow the ecliptic will follow the celestial equator. The sun will rise in the east, directly in the east, and set directly in the west, and be about midway. Because of the path that the sun follows during the summer solstice on June 21st, these are the warmest months because we have the most direct sunlight for the longest period of time. And on December 22nd, the winter solstice, these are the coldest time of the year because we have the least direct sunlight for the shortest period of time. Now, I had mentioned previous in the lecture that I can identify the pole star Polaris in the sky. Well, it turns out that even this constant I would say like a very, very reliable star used or playing such an important role in navigation for so long is in fact not constant at all. If I watch on any given evening and you can do as a little experiment is to set up a camera with a long exposure, point it at Polaris and open the shutter and let it run, I'll find that all of the stars in the north or near the north celestial pole wheel about Polaris because the axis of the Earth's rotation points most directly towards Polaris. But the fact of the matter is, as the Earth rotates on its axis, it's a bit like a top, pictured here on the left. We've all seen a children's toy top when you spin it and it processes on its axis, wobbling around. The Earth does the same sort of wobble, and in fact, what is the pole star today, Polaris, was not the pole star, for example, in 3000 BC when Thuban was the pole star. And in fact, in 14,000 AD, Vega will be the pole star as the Earth goes around in its precession. This entire motion to go around once completely takes more than 25,000 years. And so it's very, very difficult to detect this, and yet, with modern astronomical techniques, we've been able to do so. This is a phenomenon that I have personally have great affection and interest for. I find this fascinating. This is what is called the Analemma, this figure eight in the sky. These images were taken very near the equator. I'm not terribly sure whether the ruins were composited in for effect or whether it was this photo was actually taken in the vicinity of these ruins. It could be a fake. Nevertheless, the pictures of the sun here are legitimate. What the photographer did here is at exactly the same location on the surface of the Earth at noon every day, not every day, but with some regularity, took photographs of the sun. In order to find out what the sequence was, we'd have to counter out how many pictures they took. Because they do this for the entire year, a whole 365 days of the year. If we'd taken a picture every day, we'd have 365 pictures. And clearly we don't. We took some days off. Perhaps the weather was bad. Perhaps had something better to do with their time. But these are pictures of the sun taken at noon for the entire year. Well, this is some very curious motion. You may have originally, at first blush, thought, well, if you take the picture of the sun every day at noon, it should be in the same place. Well, that's clearly not true because, as we've already stated, in the summertime, the sun is higher in the sky, and in the wintertime, it's lower in the sky, and so this should account for that. But then I get this curious little figure eight side-to-side, back-and-forth motion that needs to be explained. The history of this particular phenomenon is very interesting indeed. Here's another image of this Analemma, which is the name for this particular phenomenon, except it's taken in the northern latitudes where it turns out that if you don't do it at the equator, you don't get a vertical analemma, you get one at an angle in this way, and the photographer here had to put an interesting spin on it in leaving the shutter open for a time as the sun rose on the summer solstice. That is the bright line on the left, the sun rising into the position at the top of the Analemma. And also leaving the shutter open for the sun rising on either the vernal or autumnal equinox, we can't tell which, and in the lowest position having the sun, allowing the shutter to be open for the sun rising at the winter solstice. You can produce this figure of the Analemma yourself by using a stick. That's a really interesting practice here. Follow the logic. I go outside and I face south. I know that if I am facing south, then the sun will rise in the east and set in the west. The sun will rise on my left and set on my right. So I take my stick and I stick it in the ground. And at sunrise, the stick will cast a shadow. So here's my same stick with a shadow cast on the ground in the morning. And what I do is I take that morning shadow and use it as the radius of a circle that I draw around the stick. Now I have a stick with a circle drawn around it that was the radius of the sunrise shadow. Naturally, as the sun rises in the sky, the shadow will get shorter and will leave the circle entirely. Also, the shadow will swing from the right to the left as the sun travels overhead and heads towards the west where it will set. When the sun sets, once again, the shadow of the stick will lengthen, and at some point it will once again touch the circle. This is exactly what I wanted to happen. I'm going to mark both of these shadows and find the bisector. The bisector of this angle would be the line across which the shadow would lay at noon of that day. On the very next day, when I don't expect that there's much change in the sun's position in the sky whatsoever, I'll do the same experiment again, but as the shadow of the stick crosses the bisector line, I'll mark the tip of that noon shadow. So when I mark the tip of that noon shadow, I will have essentially made a mark on the ground that represents the position of the sun in the sky on that day. I'll repeat this process over and over and over again, and when I do, the dots that I put on the ground that represent the position of the tip of the noon shadow will trace out the Analemma on the ground. The spectacular thing about this is that the Babylonians discovered this technique in 1300 BC. In 1300 BC, it was possible for them to perform this process and recognize that there are 365 days in a year. Not only that, it was possible to recognize that it's not exactly 365, that there's a little bit of variation in the year according to that. 1300 BC. I challenge you to go around and ask people that you meet on the street, how do you know how many days there are in a year? They'll say, well, they're 365. How do you know that? Well, I look at a calendar. How do you know? Well, the way that we know these things is by making observations of the heavens. And it turns out that just by observing the heavens and supplying a little bit of cleverness, you can discover a great deal about the nature of the universe at large. And this is how you discover the length of the year. The Analemma works out this way. The crossing is not at the autumnal and vernal equinox. In fact, September 1st and April 15th is when the crossing takes place. This indicates that the summertime, sorry kids, is actually shorter than the wintertime. The warm months are shorter than the southern months, or not the months are shorter, but the number of days of winter is greater. The seasons themselves are the same length, but the warm months are shorter. Okay. Worst screw up of the entire lecture series. What I mean to say is that the seasonal weather is shorter than the cold weather. And at the top of my Analemma is June 20th, the summer solstice, and December 21st, the winter solstice at the end of that. When I was a boy, my grandfather worked for Longwood Gardens, which is here in Pennsylvania, is one of the premier botanical gardens in the world. And if you have an opportunity to visit that very beautiful location, I as a young boy, spent lots of time roaming the grounds of Longwood. In the topiary garden, they have this peculiar scene here, which I think many passers-by just sort of walk by. There's not a very good plaque describing what's going on here, but you can just see in the middle of this concrete circle the bottom of what looks like almost like a coat rack. And if you follow it upward, it's hard to see because it's very much the same color as the bush, but it's quite tall. It stands as tall as I do. And there are little dots on the holes drilled in the concrete slab where an attendant comes out on a daily basis and places this pointer at a particular location based on the time, on the date of the year. Then the shadow cast by the pole tells the time. You see Roman numerals around the outside of the circle telling the time of day. The significant thing here is, in order to get the time of day right, the sequence of holes that are drilled, which are give the marking position to tell the caretaker where to place the pole, form the analemma. They're in a figure-8 shape on the ground. Now, I've described the analemma in terms of how I can create it. I know that it's due to the motion of the sun. I know that the highest extent of the analemma is on the summer solstice. I know that the lower is in the winter, but here is my question. I can explain the up and down motion of the sun with regard to the analemma. Why does it go side to side?